Welcome everybody, my name is Ricardo Vinuesa, and today we are doing it. We are facing the final boss, the Navier Stokes equations. So using all the information that we have learned in the previous weeks, including the reduced order model, being able to decompose the problem into a spatio-temporal decomposition, leveraging the POD modes, taking the reduced version of the equation and replacing it into the PDE, into the partial differential equation to get a bit of insight. Using all those tools together, we're going to look at the equations that govern fluid flow. Actually, incompressible fluid flow, we're going to look at the incompressible Navier Stokes equations, which are a very complex PDE in space and time. But we're going to try to see what is the general framework to build reduced order models with this approach. So let's look at the incompressible Navier Stokes equations. Navier Stokes equations. These equations govern the fluid flow. Incompressible. Okay, so the density doesn't change. And this is what the equations look like. First of all, we have conservation of mass, which is the divergence of the velocity vector being 0. And second, we have the conservation of momentum, which is basically that the partial derivative of u with respect to time plus the nonlinear term, which is a convection term, and this would be a u dot nabla u. This is minus the gradient of the pressure, or the pressure gradient, plus 1 over the Reynolds number times the Laplacian of the velocity. This last term will be the viscous contribution. Okay? So these two governing equations, these are the Navier Stokes equations, which represent, respectively, conservation of mass. So this is mass conservation. It's also called the continuity equation. And the second one is the momentum conservation. Okay, so as we did in the previous video, we're going to express our velocity field, our spatio-temporal velocity, as a sum of spatial modes and temporal coefficients. So we now let u, which is a function of space and time. Now u is a vector. Before, when we looked at the temperature, that was a scalar, therefore this symbol was not there, but because now u is a vector, you have u, v, and w components, now we keep the tilde, which denotes that this is a tensor, in this case a three-dimensional vector. Okay? So what we have here, because we have 3 dimensions, is that u will be approximately, let me just make sure that I can paint properly, there we go. The sum from k equals 0 to r of ak of t times uk. Now this is again a vector, because we have u, v, and w components of the spatial modes of x. Okay, and now this would be basically the base, the base flow, and this would be the mean flow. So this would be u0 of x plus the sum from k equals 1 to r of ak of t times uk of x. Okay? So if you do this operation, you will see that for the 0 mode, the temporal coefficient is a constant, right? This, when you do the SVD, you will see that the largest singular value is the first one, obviously, because they're sorted by descending order, but it's much larger. This means that this is just the mean. It doesn't have a fluctuation component, it's just the bulk of the flow, that's the mean. And then we put all the fluctuating quantities on this summatory here, starting from k equals to 1. So over here, what I have is this sum, okay? This I'm going to call plus, because to make the derivations a bit shorter. And this means that, we can really express our spatiotemporal function as spatial modes and temporal coefficients. Now, an important thing here is that we're going to be using the pressure gradient together with the continuity to basically satisfy continuity. And that will be a way for us to ensure that the modes also satisfy the boundary conditions. So in other words, note, the POD modes are linear combinations of the snapshots. And therefore they satisfy the boundary conditions of a star boundary conditions of these equations, right? So the POD modes satisfy the same boundary conditions, and they are solenoidal. They're also divergence-free. They are divergence-free. What does that mean? That means that combining the divergence equation and the solenoidal property of these POD modes, we can make sure that the pressure is not influencing our evolution of our reduced order model of our POD modes. So the pressure term, which is responsible for ensuring continuity, vanishes. Okay. Now we can substitute the POD expansion into a star. So basically this expansion here into the momentum equation. So substituting the POD expansion into star, what I have is the following. I'm going to try to go term by term, put this expansion on U on each of the terms of my momentum conservation equation. So what I will get is now the partial derivative with respect to time, okay, of U0 of x plus the sum from k equals 1 to r of ak of time and uk of x. Important note, obviously this term and these terms are constant with time, so that means that they will come out of the derivative in the next step. And that's equal to, and of course we are now moving the convective term to the right hand side, okay, so that minus here will be associated with the convective term. So that's minus, and let's put it here minus, and this is U0 of x plus the sum from k equals 1 to r of this. Okay, remember that this we call it plus, so that's the sum of plus here. Okay, dot nabla. And we will have here the same but with a different index, because remember when we look at this nonlinear term, I want to be able to cover all the nonlinear combinations, right? So that means that I will have the same expression but with a different index. So what I will have here is basically U0 of x, which is again the mean flow, plus the sum, now from j to r of plus, of the sum plus. And now the last term is the viscous term, which is 1 over the Reynolds number times the Laplacian of U0 of x plus the sum from k equals 1 to r of plus. Okay? This looks a bit ugly, like there are many things going on, but we can actually work things around a little bit. In a nutshell, we're going to do the same that we did before. We're going to take the things that depend on space only, right? And then those will come out in the temporal derivatives. Things that depend only on time will come out of the spatial derivatives. The spatial derivatives are going to be here by nabla and the Laplacian operator. So let's exactly do that. What I have here is the sum from k equals 1 to r of ak dot of time times uk of x. Okay, so of course, interestingly, when I calculate the temporal derivative of this guy, which is constant, I have a 0, so the only term remaining is actually this one. So that's, and the temporal derivative is in this dot, so the UK has effectively come out of the time derivative. So the partial derivative of the mean flow goes to 0 because that's a constant, and the spatial modes are actually coming out of the temporal derivative. So I have this, and now what I have is, well, to operate a little bit in these brackets here. So I'm going to have a bunch of terms, right, that come from all the cross products. So what I have is minus u0 of x times nabla times u0 of x minus u0 of x dot nabla sum from j equals 1 to r of plus minus, and now here I have a double sum. This would be the sum from k equals 1 to r and the sum from j equals 1 to r of basically the term plus dot nabla plus, okay, minus the last term of the whole products, of the 4 products that I was going to get. This is the sum from k equals 1 to r of plus dot nabla u0 of x plus, let me get this out of the way, 1 over the Reynolds number times the Laplacian of u0 of x. Since u0, that's the mean flow, depends only on space, the Laplacian, it doesn't cancel, obviously, I need to calculate the Laplacian of the mean flow. And then what I have also is 1 over the Reynolds number times the Laplacian of the sum from k equals 1 to r of plus, okay? Okay, we're getting there. We just have a bunch of terms and equations, but if you remember what we did before, after we pull out the terms that were constant out of the derivatives, what we did was to apply the inner products on both sides in such a way that I can then cancel the cross projections, right? So we take the inner product in space. In space with ui of x, and remember we use the orthogonality, so the orthogonality means that uk uj is going to be the Kronecker delta kj, which is 1 if k is equal to j and 0 if k is different from j, okay? So if we do this, and that's now, there's quite some pages of algebra, we're going to skip them, you can just look at the final result. But if you do all of this, what I will end up is with a series of ODEs for the temporal coefficients. So what I have is the ai dot, function of time, the sum from k equals 0 to r of bik ak of time, plus the sum from k equals 0 to r, and the sum from j equals 0 to r of some coefficient Cijk, and this is ak of time, and this is aj of time. Okay, this is a quite complicated term, but this is in principle a way to find the temporal coefficients of those POD modes through Galerkin projection. Now this would be a bunch of ODEs which contain the temporal evolution of the POD coefficients. Okay, and this one over here, this is basically a nonlinear term that comes from the nonlinear term of the governing equations. So this is the nonlinear term from the nonlinear u dot nabla u in the Navier Stokes equations. Okay, the only thing that I have left is to define the bik and the Cijk. These are just coefficients, okay, that have to do with all the different components that I have for my temporal evolution. So if you do all the math, what you will get is bik is the inner product of the gradient of ui of x. This is the gradient of uk of x. Whereas Cijk, that's the inner product of ui of x with now uj of x dot nabla, and this is now uk of x. Okay? So that's a little bit the idea. Okay, let's recap what we have done. We started with the Navier Stokes equations, which are complex PDEs, right, in space and time. We then express our solution in terms of POD modes, which are spatial modes and temporal coefficients. And then that allows me to reduce the dimension. But eventually, if I want to have a reduced order model, it's not just enough with reducing the dimension. I also want to have something for the temporal dynamics. What happens with my temporal dynamics, right? These spatial modes don't change with time, and these temporal coefficients are the ones that are going to give me the temporal dynamics of the system. Then I just replace this expansion into the PDEs, into the Navier Stokes equations. I use properties like extracting the terms that do not depend on the derivatives, and then applying inner products on both sides, exploiting the orthogonality of the modes, and then I simplify after a bunch of algebra, and I end up with this. So in fact, the whole spatiotemporal system, which is, a bunch of PDEs with very high complexity, are reduced to a bunch of ODEs, of ordinary differential equations, which are much easier to treat. It doesn't mean that they are always treatable. In fact, in general, they're quite complicated because evaluating these terms is not straightforward. And even if one has those terms, evaluating these ODEs, this system of ordinary differential equations, that's also not easy in general. But this is one approach to reduce the dimension of the systems. Something that has been happening in the recent years is to, for example, do POD. And if you do POD, then you have fixed the spatial modes, and then you only need to find the temporal coefficients. And for the temporal coefficients, people have been using deep learning. So for example, LSTMs, recurrent networks, more recently transformers, different ways of obtaining these temporal coefficients. And then you get the spatial modes, which are coming from the standard SVD, from the standard POD, and the temporal coefficients, which come from the deep learning tools. And then you don't need to do all of this, which is complex, especially the solution of this ODE system, which is certainly a valid approach. An alternative, and that's something that we have proposed in my group, and that's something that we believe has tremendous potential, instead of doing POD, you can use beta variational autoencoders. So let me give you a little recap. If you do a beta variational autoencoder, what you can do is do like POD, but with non-linear methods, with an autoencoder. So, and there are many videos in the channel where you can go in details on how autoencoders work, but in a nutshell, you basically obtain a latent representation of your system, a bunch of temporal coefficients, leveraging nonlinear operations here, right? And because these systems are in general chaotic and high-dimensional and nonlinear, these nonlinear operations in the encoder and the decoder allow you to more effectively compress while retaining the optimality and orthogonality properties of the POD. And this is something that we show in our papers about the beta variational autoencoder. So, and there is a good paper by Eivasi et al. From 2022 in Expert Systems with Applications, where we explain in detail how to do this dimensionality reduction with beta VAs, basically doing the nonlinear POD. But that's just about the dimensionality reduction. Once you have reduced the dimension of your system, you want to be able to integrate in time. You want to do what I just mentioned that we have done now with Galerkin projection. And what we do in our research is to use in this latent space, which is basically a bunch of temporal coefficients, then we use LSTMs, blah, blah, or transformers. And that's the key. When we combine the beta VAE to do the nonlinear POD, plus the transformer to do the temporal predictions in such a way that you can capture the multi-scale character of turbulence, then you have a pretty powerful combo to really build for real nonlinear reduced order models for chaotic flows and for turbulent flows. And that's something that we have published in a couple of papers. This is Solera, Rico, et al. And this is in Nature Communications 2024, and also Wang This is Juning Wang in my group, et al. And this is International Journal of Heat and Fluid Flow, also 2024. Okay? This is more about the fundamental development of the method, and this is an application to a turbulent flow, to a 3D turbulent flow around an obstacle. So everything that you have seen in this series is helpful. These are the fundamentals. This is about POD, dimensionality reduction, and Galerkin projection. And let's say that the more recent developments in this area come from these references. Okay? So you can do dimensionality reduction non-linearly with beta BAs, maintaining the optimality and the orthogonality, and then you can do the integration in time by combining the beta BAE with a transformer. Okay? So that's everything that I wanted to talk about today. Please feel free to reach out if you have any questions. There's a lot of exciting stuff happening all the time in research in this very, very active area. So I'm always happy to discuss ideas and collaborations, and see you in the next video. Thank you so much. Bye-bye.